Hello everyone. I'll be waiting for a couple of minutes before I start the class just to see if anyone is joining. Yes, I hope you're able to see my slides. Okay. So last class, we had stopped our discussion about assignment one and two. So those questions were from the week one and week two classes, right? Now we'll be moving on with the class four. Okay, yeah, I think my slide, I haven't turned on the video. I have done that now. Yeah. So now we'll be moving on with the third class. Sorry, the fourth class. So here I'll be first discussing about giving a brief description about what we learned in class. I mean, third week, what sir had taught, and then we'll be also discussing the assignments. So without any delay, I hope the questions from assignment one and two were easy. Those were mostly like some numericals were also there, but it was kind of easy, right? Yeah, so then we looked into multi-sign and all that was from assignment two. So yeah, now it's class four and produce. Yeah, so a brief description, talk about what we learned in that week. And yes, then we'll look into the assignment. So let me just take the book. We'll be looking into what linearity is, what stability is, what repeatability is. Then we will looking into data validation. There we also saw few examples, right? So basically, this last week you have looked into data validation where you saw Kramer-Kronig transforms and then how we transform data in impedance to admittance form. Then the challenges in KKT validation application, then alternatives that is direct integration of KKT. Yeah, that's what we had looked into. So basically, last week it was more about last week meaning the assignment in assignment questions in assignment three were based on data validation, where you learned what is KKT, then you saw many examples in them, right? And then how to transform impedance data versus admittance data. So basically transformation. Then what are the challenges in KKP? Then the application, and we also saw an alternator. The alternator was but what the topics based on which you are supposed to solve assignment 3. So this is something that we need to know what is repeatability, what is linearity, and what is stability. So those are the important terms. I mean, important term meaning. So in order to check whether the system is linear, stable, and repeatable, we are actually performing KKT. Okay, and then we'll be seeing some examples also. So yes, now what is repeatability? So repeatability meaning we have to check the reproducibility. That means when we are doing the same experiment multiple times, we should get repeatable answer, right? So basically repeatability means we are checking the reproducibility because we cannot come or get a confidence on the data based on a single run of experiment. We should do at least two. So to check the reproducibility, we'll do at least twice. Now, what do you do when you do reproducibility test? We should get meaningful data. Both the time it should look reproducible means it should be almost matching. So yeah, that is about repeatability. So when you do that, we should get a meaningful data. Yeah, and if you're doing more number of times, it's well and good. Now the next one is linearity. So in linearity, what do you do? You are applying a DC potential on which you are superimposing a small amplitude. So that's how we get the input signal. It might be potential or current. That is the input you're giving. So the ESC not value should be small enough such that the system is linear. What is linear meaning? So if I apply some EAC naught, correspondingly I'll get ISC naught as the output, right? So that's when based on the EAC naught and ISC naught, you're calculating the impedance and plotting. You get the Nyquist plot. Now what if this EAC naught value? I'm just doubling it, so it becomes 2 EAC naught. So what I'm expecting is that the current value should also be getting doubled by 2. It needs to be also needs to be doubled. So only in that case, when you do impedance that is CAC naught by IAC naught, the impedance won't change. So even if you change the in DC potential, the current should also be increasing by the same factor so that overall the impedance wouldn't have any change. So in that case, we say that the system is linear. In cases when that doesn't happen, we say that the nonlinear effects are coming to play and the system is nonlinear for your applied potential. So yes, so what it means is EAC naught should be small to get a linear response. So how do you do it? You obtain the spectra at 2 EAC naught. Example 5 millivolt and 10 millivolt. Example, I am running the experiment. Now the impedance plot that I am getting should match in both the case. The EIS result should match within the noise limit. In that case, we say that EAC naught is small enough and system responses is linear. there's a small mistake what I said. I would have said you have to apply two DC potential. It's not two DC potential, two AC amplitude that I was talking about. It is a mistake from my part. So you have to apply two AC potential. So DC wouldn't change, but for a given DC, when your amplitude changes, it should be within the limits such that the system will be still having a linear response. Okay, I just wanted to correct that. Yes. So that is about the linearity. So the next one is stability. Yeah. So stability meaning we are assuming that the system becomes what to say the system remains so stability means system is unchanged during experiment. That is, the system doesn't undergo any changes that is during the reaction period. So how do we now confirm that? Now, how do we confirm that the system is stable during the experiment time? So usually we are assuming that the impedance will take around 15 minutes for an impedance experiment to be done. So if the system has changed significantly during that period of time, so the data that you get by doing this experiment will be incorporating that effect as well. Okay, and that can give you an incorrect interpretation about the data you have got. So, how do we what should we do in order to avoid this? So, for the same experimental condition, for the same setup, we should repeat the experiment. How this is different from reproducibility or repeatability. Repeatability, where we are changing the system, we do one experiment, we dismantle it for the fresh electrode or something, we are again setting up, we are doing the experiment. Here to check the stability, that is the during that experiment, the system is not changing. In order to understand that, what we do for the same setup, we'll run an experiment. Now, once the impedance is run completed, we'll repeat that impedance on the same system once again. So ideally, that result should not have any change. So that will ensure the stability. So how do we do it? If system changes significantly, so the system is changing during the experiment, data will be including the effect of these changes, and this will lead to incorrect conclusion. So, to ensure no changes is happening, what do we do is we are repeating the experiment for the same setup. So that's the difference between repeatability and stability. Because the explanation of repeatability and stability can seem little confusing regarding the repeatability of that experiment or redoing the experiment, I should say. So there are two terms that you need to understand, three terms that you need to know before you go for KKT validation. One is repeatability. That means the experiment that you're doing and the impedance result, you need to, interpret it. You should also make sure it is repeatable. So that is the first one. The next thing is linearity. Linearity means for whatever the EAC not or the amplitude value should be such that within the noise limit, even if you're changing the EAC not and going, the experiment should be you're getting similar result within the noise limit. And finally, the system should be stable. That means during the experiment, system should not undergo any change and it's stable. So for that, after one experiment is done, we'll be repeating or we'll be redoing the experiment on the same system just to see that the impedance value is not changing. Okay. Yeah. Now the next one is we have to understand. So these three are conditions that you need. So, in order, there is a test that is available in order to validate EIS data. In order to validate EIS data, there is a technique, and the technique is KKT or Kramer Kronig transform. So, what this done is the EIS data that you get will be subjected to KKT in order to validate the EIS data. So, what do? You have experimental result for the frequency, the real part, and the Z imaginary. You will get all the three. Now, what you will do is you'll take frequency and the real part of the impedance, and then you this will be fed to KKT. Now, the output it will give Z imaginary value, and from the KKT. Using the KKT method, you'll be getting the Z imaginary value. This Z imaginary that you get, and then this experimentally obtained the Z imaginary, they should be same or within the error limit. I mean, they should follow. They should be same. Only then, if that is the case, you do this and you're validating the impedance data, and you can say that the system is linear, causal, and stable. And if you don't get this, okay, yeah. So if you get like this, we say that the system is linear, stable, and causal. If the signal we get is caused only, okay, uh, sorry, just give me a moment. So now the next thing to understand is what is causal. Because causal is not a term it's introduced before. Let's write it in the next page. So causal means when you're applying a small perturbation, you're applying a perturbation and system shows a response, right? System gives response. So according to causal, I mean the cause. What causality means is this input, this signal we get, okay, that is solely because of the applied perturbation. This means no noise or any disturbance is affecting the result. Then we say that the system is causal. If the signal we get is caused only by the input perturbation we apply, then we say that the system is causal. So as mentioned, what we do is we are doing this to validate the data. We do experiment. We get frequency versus ZRE and Z imaginary part of the impedance. We feed any two, that is frequency and ZRE, or frequency or Z imaginary. Any two. I mean, with frequency, either one of them, either ZRE or Z imaginary. We feed it to this software. Okay, and then it will give an modeled value of Z imaginary or measured value of Z imaginary. And if it matches well with the experimentally obtained Z imaginary impedance value, we say that the system is linear, causal, and stable. So similarly, we can also use frequency with Z imaginary value. So then we can estimate the ZRE value and compare those with the actual value. So there are also cases. So here now we talked about feeding impedance to do KKT. So there are also cases where instead of impedance, we can also feed admittance, that is YRE and Y imaginary instead of impedance for the KKT validation. So we'll be also looking into the case where we'll be using impedance form and where we'll be using the admittance form. Okay, that is a brief description about what exactly are we doing. Now we'll also just look into what is the Kramer-Kronig equation? Like we said, it's feeding into a system, but what is the equation? I'll just simply write down the equation for KKT. Okay. So Z imaginary omega minus 2 the omega by pi 0 to infinity Z R E of x minus Z R E of omega x square minus omega square dx. Now, what are the terms in this? So, Z imaginary, okay, at a particular like at a particular frequency. So we know what omega is. Omega is 2 pi f. So we have frequency was Z RE was Z imaginary. So the x corresponds to the different values of omega value vary, and Z RE at particular omega, that is Z RE omega. So that is also substituted and we get the Z imaginary value. Similarly for Z RE omega, it becomes Z R E infinity plus 2 by pi 0 to infinity x into Z imaginary x minus omega Z imaginary of x square minus omega square dx. So yeah, these are the equations that are used in order to find out the imaginary and the real part if you are using the KKT transform. So there is something that we have to understand that these are not necessary but a sufficient condition. Which one? That is linear, stable, causal. Yeah, so now linear, stable, and causal. Even the other three conditions are sufficient, but they are not necessary. These are sufficient and not necessary. Why we say so? So even if the system is linear, stable, and causal, then it will be KKT compliant. Okay, that's what we checked earlier. Now, but if the system is response is non-linear, it may or may not be KKT compliant. So that means that it is not a necessary condition but a sufficient condition in order to validate the EIS data that you have got. So what exactly is happening is that only the real part of the EIS data is measured and the imaginary. So it is not like we are just measuring the real part and not measuring the imaginary part. So we get both the real and imaginary part, but we're feeding only the real part along with the frequency to the system, and then we get the imaginary part, and then we compare that with the experimentally obtained imaginary data. So they're using a transformation integrals in order to evaluate the same. Okay. Now we'll be seeing some examples. So now there are some issues with the data acquisition. Let's see that and then move on. Issues of data acquisition. So what are the problems? The first one, reproducibility. So why reproducibility is a problem? So EIS is a sensitive technique, right? I'll write and go ahead. So EIS is a sensitive technique. So during the process, the electrode-electrolyte interface can change. And this can be because of the electrode preparation, the electrode purity, the reference electrode position. Because of all of this, you can see that the what to say, uh, you may not be always able to get. There's a challenge associated with getting reproducible data. Long electrode stabilization time can also result in affecting the reproducibility of the data. Now, if oxide film is growing on the surface of the electrode, the film thickness can change, and this can also affect the response. So, different wait times between the measurement at each frequency, this can also be another possibility. So, altogether, EIS is a very sensitive technique. So, getting a reproducible data is very difficult. But on the contrary, the PDP, chronoamperometry, chronopotentiometry, everything, or CV, this not chronopotentiometry, chronoamperometry, or CV can help us yield data with good reproducibility. And now the next problem is signal to noise ratio. Linearity requirement. So first, let me write down for the first one. So EIA is a very sensitive technique. The electrode electrolyte interface changes. So this can be because of the electrode preparation. This can be because of the electrolyte purity and the reference electrode positioning. Then another thing is long electrode stabilization time. So this can also affect the reproducibility of the data. Then different wait times. So different wait time, that is between the measurement at each frequency. Between that we will be having a wait time. Okay, so overall, ES is a very sensitive technique. That is, reproducibility is one issue associated with data acquisition. The next one is signal to noise ratio. Signal to noise ratio, linearity, and experimental duration. So when you're giving small amplitude, what happens is signal to noise ratio perturbation, small amplitude perturbation, signal to noise ratio is going to be poor, and that affects your data. And the next one is if you're giving large perturbation also, non-linearity effects can come to play. Now, when you're doing series of experiment for a given system with a series of experiment, now we have to vary the amplitude and then need to identify the range of amplitude in which the system is behaving in a linear way. And we are also having signal to noise ratio in our control. Now, duration of single EIS run, it depends upon the frequency range in which the experiment is done. So, it also depends upon the lowest frequency up to which you're going and number of points per decade. So, if you're going to lower and lower frequency, it will take more time in order to acquire the data. So, for low frequency and long experimental duration, and if the noise level, because that the noise level will be very high at low frequency region. Thus, in that case, how to overcome that? We can give multi-sign wave in order to reduce the effect of noise. So this is the next problem which is associated with the data acquisition, and that is the signal to noise ratio, linearity, and the experimental elimination. Just to write the key points, you apply small perturbation amplitude. This leads to poor signal to noise ratio. So when it's large perturbation amplitude, what will it do? It will result in nonlinear effects. So we have to identify range of amplitude in which the system can perform without any linearity, and the noise level also less. Then the next one is duration. This duration of EIS time, it depends on the frequency, in particular the low frequency, and also the number of points per decade, which we already discussed. That is within each decade, like 100 and 1000, how many points are taken, like that in between each decade. So when you're going to low frequency regime, it will obviously take longer time to have more points per decade, because already in low frequency region, it takes so much time in order to conduct the experiment. Uh, so high frequency, it gives more information about the double layer structure, and low frequency, it is giving more information about the kinetics and mass transfer. We are already seen. So signal to noise ratio, linearity, non-linearity, because of the amplitude and the long duration. Okay, that is when you have at small frequency, duration time increases. Noise can also increase because of that. Okay, noise level is high at low frequency. So in this case, how to deal this? We can use multi-sine wave. So the several sinusoidal cycles must be employed to obtain a good signal to noise ratio, and this increases the duration of experiment. So this is about the, yeah. So now let's see about the data validation. So when it comes to like which all cases the system is KKT compliant, which all cases not compliant, despite saying that the system needs to be linear, causal, and stable. That's what we're going to see. So the first example that was shown was good quality spectrum. We are making a data. So something that you have to understand is you have an impedance spectra which is generated using electric circuit. So electric circuit containing only passive elements. Passive elements means resistor, capacitor, inductance. Okay, this case where we are using resistor, capacitor, inductor in order to fit any experimental EIS data, then we say that the system is KKT compliant. This case system is KKT compliant. Uh, so we have, so for any case, something like this, we have already seen such case in, I think, in first session, where we saw that this can be fitted using something like this, right? Where this is a solution resistor, this is that R1, this is R2, and the C1. So, what has been understood is that if the experimental data is fitted using any of such passive elements, this is going to be KKT compliant. So, obviously, you have to do an experiment, you get the data and you fit it in, you'll get a better understanding on what is meant. Now, if we have, what you have to do is, you'll have frequency Z real and minus Z imaginary. You will feed this column and this column into KKT, and the KKT will give you measured value of Z imaginary KKT. It will give value. And now you are comparing this value and this value. So if they are reasonably, fitting with each other, then we can say that this KKT compliant. Now, so now, Sir had shown an example where your data is truncated after a point and you're trying to get the KKT compliancy. So we see that the low frequency regime, the KKT, the measured value and the experimental value is not meeting with each other, or they are not meeting with meaning they're not overlapping. So we may you actually flag it off as KKT non-compliant, but in actual case it was KKT compliant, and why it was flagged off was because we don't have the complete range of data. So always when you're doing impedance, it's always better to take the data at low frequency regime as well, because sometimes the KKT system can flag the system off as non-compliant because you are having incomplete data. So the solution for that is to take the data in the entire range of frequency, so that you can say that you can actually fit it properly. Okay, so I just write the key points, and that would be data at low frequency or low what to say omega value. It's not available, not available because of the long time, poor signal to noise. Okay, because of this reason, and you have only data available up to a range of frequency. So what if you're trying to if you try to attempt, if you try to validate the incomplete data without extrapolation, so there are chances that data can be flagged off as KKT non-compliant. So in that case, what you can do is we can actually extrapolate the data. But this is having its own limitation. We cannot do that. So it is always better. The solution, best solution, if I say it would be to obtain data at low frequency and validate data without extrapolation. So if you remember what Sir had also discussed one example in the class, and that was something like this. It went like this. Sorry. So you don't know where the data is ending, or because it's not actually completed. So if you do the KKT compliance, so you will get something like this. It was the example you showed. In different cases, so you may actually think the data is not KKT compliant, but actual reason being you have not taken the data in the entire range of entire range of frequency. So that's why you are getting that KKT non-compliant. Now the next case is KKT for unstable systems. Yeah. So KKT for an unstable system means if your system becomes unstable during the what to say if your system becomes unstable during the data acquisition period, KKT can successfully say that the system is unstable, sorry, non-compliant. So for an example, what they had done was instead of giving a stable DC potential, they were ramping the potential. So ramping, or they were drifting the potential. So what happens is when system is drifting off, so ideally, you will be thinking you are superimposing the DC potential and with an AC potential and doing the experiment. But in actual case, instead of going like this, it goes slightly like this. So the AC is getting superimposed over this. So this is not a stable system. That is, its potential keeps on changing over the time. Yeah. So such a system was used, and onto the system we check that if it is KKT compliant. When you did that in the low frequency regime, we see that the model and experimental data, they deviate. So this has been attributed to the fact that the system is not stable. So in order to understand that, we already know that the potential is not stable. So basically, we are knowingly doing something and trying to study the effect of that system. So for that, we are drifting the potential or ramping at a potential ramp rate, and then we are trying to study how the impedances vary. So this is one case. So here, what we are doing is we are introducing a superimposing a potential ramp. We are using a potential ramp, and so at low frequency, it's subjected to KKT, and the results what it shows is violation of the stability. So this is one example. And another example is instead of applying so now the next one is example for the non-linear examples. So for non-linear effects, what we are doing is we are giving a large amplitude perturbation. So the large amplitude perturbation means this EAC naught by IAC naught becomes a large value. Okay, and this used to collect the EIS data. So if the data we acquired using this large amplitude is different from the data we get it from a small amplitude, we say that the nonlinear effects are manifesting in the data because of the so in simulation it's possible to incorporate these nonlinear effects and calculate the EIS response. So for that, what again, sir had given another example. If you remember, if for a small potential you were getting, I mean DC bias, you were getting an impedance like this, but at a higher magnitude of amplitude of 300 millivolts, you were getting something like this. So from this, we say that the nonlinear effects have come. in to play. And similar in this case also, in the low frequency, low and mid frequency, deviation is seen between the measured and experimental value. So from this we say that the system is non-linear, so it is not KQT compliant. So these are the cases which we saw now. Like when you can flag of the system as KKT non-compliant. One case was when you have an incomplete spectra. If you have an incomplete spectra, it can, because it's taking a longer time for your experiment, or there is noise at low frequency regime and all, we are actually truncating the data. And in that case, one way is to do extrapolation and do, but in that case, it has some difficulties. It can flag off as non-compliant. So what we have to actually do is we have to obtain the data even at low frequency regime and then validate the data. So this is one example. Then we say the unstable system. Unstable system is the case where the system keeps on changing or so it's not done with a stable potential. So what we are doing here is, instead of applying a DC bias, we are ramping it, or it changes with time. And then when we do the KKT, we see that the model and the experimental value show deviation at the low frequency regime, and this difference has been attributed to the nonlinear effects. Now, same way, we can apply that this has been attributed not to nonlinear system but an unstable system. So we saw unstable system in then and then like what to say, incomplete spectra, and the next case was the nonlinear effect. So in nonlinear effect, we are trying to apply two different DC amplitudes, and we see if the data is actually overlapping. But here in this case, no. At higher amplitude, we see that the system deviates significantly from the small amplitude perturbation based impedance, and we say that the nonlinear effects are come to play. And all these problems can be flagged off by the KKT method, and we can say the system is either non-linear, it's not linear cause it doesn't satisfy the conditions. Now there is another case where we will be transforming the data from the impedance to admittance form. So when can we feed the impedance? When we need to feed admittance code to KKT compliant. Okay. So as an example for that, in the low frequency regime, in simple words, in low frequency regime, if your data shows a negative impedance for the real part, that is, your real part goes to the fourth quadrant, not fourth, second quadrant. That's because the negative x-axis, the real part is going to negative x-axis. In that case, we have to go for the admittance one. Let me explain. Low frequency. In the low frequency impedance, those negative values at some DC potential. So the example that sir had given was something of this kind. So here in the low frequency regime, it is going to the second quadrant. So when such a data, okay, this is actually the impedance data, ZRE versus minus Z imaginary. When data of this form is subjected to KKT, what will happen is the original and the transform data match well in high and mid frequency regime. In low frequency, what happens is the transformed data appear as a mirror image. So in this case, we may say it's not KKT compliant, but actually the case is not that. It's because it's going to the negative domain. So for example, mm, your data is something of this form, okay? And when you do KKT compliance, you will get something like this. It matches well at low and mid frequency, high and mid frequency, but at low frequency, you get some kind of mirror image for both the ZRE as well as Z imaginary. So from this, what I understand is if system is stable under potential static mode, then KKT validation must be done on admittance mode. And same way, if system is stable under galvanostatic mode, then KKT validation must be done in impedance mode. Our data is stable in both impedance and sorry, if the data is stable in both admittance and potential static mode, then the validation can be done on either admittance or impedance. So, so these are the key points from this. That is, if it is potential static, you have to do it in admittance form. When it's galvanostatic, you have to do it in impedance form. If it is stable for both, we can use either of the method. So this is one case. Now the next case, what if the impedance values are close to zero? What will you do? If the impedance value is very close to zero, it will have significant amount of errors. This significant amount of errors, that is because data is stored at finite precision. Corresponding admit so impedance value is already close to zero. So and it will have round of errors. Now if I am taking the if I have to do it in admittance form, already it has error. Now when we are taking the reciprocal because we need an admittance form, the error value is again going to increase significantly. So this will lead a mismatch between the original and the transformed data, even though the original data is KKT compliant. So what can we do in that case? So in this case, we can do is we can add a small resistor in series, then validate the data using KKT because this will reduce the numerical error value that is associated. So point is impedance value is close to zero. It is having significant error, and in that case, Corresponding admittance value, they have large error, and this leads to mismatch between original and transform data. Even though the data is so, how to overcome this problem? Add suitable resistor in series and then listen carefully. So, this will help you reduce the impact of numerical associated with converting small numbers. Yes. I hope this is clear. Now we have another alternate method also. This is the first one. The alternate method is that we can add a small resistor in series in parallel. Instead of adding in series, we can add in parallel to the impedance data. Process entire data to have positive real value. So both the solution can be used either in series or in parallel. Now this has its own challenges. Now let's look into the challenges. So the challenges being, so the first one is sufficient care must be taken when you are cropping the data. The next one being, so data must be validated in suitable form, either in impedance or in admittance form. So we know that if the values are very small, we have to go for impedance. Either we have like we cannot go for admittance form. Either we apply resistor in parallel or in series. That problem. Now, if the data is going to the second quadrant, the real part, then again we have to go for admittance part. Only then we'll get a KKT. I mean, the KKT will flag it off as linear, stable, and constant. So now, if we have data available only in the limited range of frequency frequency, then even if the data is linear, stable, and causal, the system will flag it off as KKT non-compliant. So even though we can perform extrapolation, that is the best solution is to acquire the data in the entire range of frequency. Okay, that's something else we had looked into now. I'll be writing the same. The assumptions that we say are just sufficient, not necessary conditions. So this means that any violation of KKT indicates that one or more assumption is violated. But compliance with KKT does not guarantee that is that doesn't guarantee that all of the three, that is linear, causal, and stable, are satisfied. So in that case, we cannot say it's necessary, but a sufficient condition. So violation of KKT, it means that more than one condition violated. But compliance with KKT doesn't imply that system satisfies all assumptions. So there are also cases, there are cases when linearity is violated, and but still the data is KKT compared. Yeah. Now, experimental and the simulation results is that KKT is always sensitive to the presence of any noise. Okay, so that is called causality, and it's also sensitive to stability. Still, only limited number of cases it is sensitive to the nonlinear effects. So, problem arises when the data is problem again arises. So that's another point. So that's a problem. Like stability kind of it flags off, we saw it with the ramping. Causality noise is there, that also can identify. But in the non-linearity, it may or may not identify. but only in limited case sensitive nonlinear effects. So problem is arising when the data is available. Next problem, data not available, entire pH, entire frequency range. So that is another problem. We can either extrapolate it, but it may or but it has its own difficulties. So it's always better to get the data in the entire range. But if you have a truncated data and you're using it, it can give you a non-compliant. So that is another problem. So KKT validation gives the confidence that the system is linear and stable and causal, but not necessarily linear. Okay, so that is something you have to understand. KKT, this means stability. It can identify causality, can identify, and when it is linear, may or may not. This is about the challenges. The first challenge, where the cropping comes with its own problem, or then data must be validated in suitable form, impedance or admittance. Now, limited frequency regime, if data is available, you can flag it off as non-compliant. So you may either need to acquire data over the entire range, or we may need to extrapolate. These are sufficient and not necessary conditions. There are cases when linearity is violated, even though system is KKT compliant. So KKT is also sensitive to presence of noise. So these are the problems or the challenges of KKT. The next thing is application of KKT. After this part, we'll be looking into the assignment questions. So the first one is data validation. So if your data is not KKT compliant, uh, what are the usual reasons for that? You can say the culprit. Okay, the culprits I can say either noise or causality. Okay, instability, or I can also say the data is not acquired over the entire range of, okay, non-linearity is also another thing. And data not available over entire frequency range. Okay, so the first idea application is data validation. So you can identify if there is noise, instability in system, non-linearity, or or otherwise it's because you don't have the data in the entire range. System is stable in potential static form, you can apply it in the admittance form, and if it is in galvanostatic, impedance can be done for in impedance mode. So that's usually for batteries and fuel cells. So if the data is containing impedance whose real part is negative, then KKT must be performed only on the admittance form. Or we have to modify the system by adding a small resistor in parallel so that the entire value shifts to positive. So this point we haven't written. If data contains impedance whose real part is negative, then apply KKT on admittance form that we had already seen, or Modify impedance. How do I modify the impedance? Add small resistor in parallel to the real value of impedance. This is usually done at low frequency. So there are two ways. If you're applying the data is going negative, but you can either do it in admittance form or you can add a resistor in parallel to the real part. Okay, so that everything shifts to the positive. So with this, we have come to the end of understanding what KKT is doing. So basically, it is used to flag up the linear, causal, stable systems. Okay, flag the system. So now we will see or try to understand. Yeah, so before going to measurement model approach, we will try solving the assignments. This is assignment number 3, which happened last week. I think that due date was 2 days back, right? Yeah, it was on 11. Friday? No, Wednesday, I think. Friday. So the first question, you have in total 10 questions. So the first question, when EIS data from following circuit is validated using KKT by integration, the transform data didn't match with original data. What is the reason? Yeah. So they have given you a system like this. Okay. R1, P2, R2, R3, R4, P3, P4. So when EIS data from the following circuit is validated by KKT using integration, the transform data didn't match with the original data. Now, what is the reason? So, options are given: large amplitude perturbation was used, data was transformed in impedance mode. data was transformed in admittance form. Option B, frequency range is limited. So now let's analyze the options. So we have a circuit. So before that, in the same module, there has been an introduction given to measurement model approach. Okay, so what does the measurement model approach is? When you are modeling a system using a resistor, capacitor, or inductor combination, or if you're able to model the experimental data with a reasonable fit, then the data is normally KKT complete, right? So ideally, it means that this should be KKT compliant because if we are using able to model this properly using the resistor capacitor combination. Now, it is not matching well. What is the reason? So first option is large amplitude perturbation was used. So the non-linearity may or may not be flagged off by the KKT offline by the KKT. So we can keep this as an option, but we are not sure. Any one is an option. So this may or may not be. It may be able to flag out off, or it may not. Okay. Now the next option is data was transformed into impedance form, and the option C is data was transformed in admittance form. So, transforming data in impedance or admittance form will not have an effect on KKT components unless or until, okay, that comes into play when your real part is going to the negative side, okay. But apart from that, or if the values are very small and you do it in admittance form, this error can happen. So, admittance form, so that those are the cases. So, those are not described here. Frequency range is limited. Yes, we did see that if you don't have the data in the entire range of frequency, it may be flagged off as KKT non-compliant. So the right option here is frequency range is limited. Not first reason because it may or may not be. There are cases when non-linearity cannot be completely flagged off, and here we are using resistor and capacitor. And so if that is able to fit it well, then large amplitude may not. I mean, uh, large amplitude may or may not be flagged up by KKT. But when frequency range is limited, we are sure that this is a problem. Next question. Is condition of linearity or stability or causality is violated, then EIS data will not be KKT compliant. True or false? So the first thing we need to understand is KKT non-compliant if we get. This means either non-linear, not linear, or not stable, or not causal. That is, the noise is affecting the system. But so this is possible. If it's not KKT compliant, then these can happen, right? If the system says it's not KKT compliant, then we can be sure that if one of them is surely possible. But if the system is, if the condition of linearity or stability or causality is violated, then it may or may not be KKT compliant. Why? The vice versa not applicable. This means linearity stability, causality, they are not necessary condition. They are simply sufficient condition. So, if the system is flagged off as non-compliant, we can be surely sure that either non-linear, not stable, or not possible. But vice versa is not possible because they are the sufficient condition, not necessary condition. So, the option is false. Okay. Now, the third question, KKT equation relates real and imaginary part of impedance, magnitude and phase of impedance, real part of impedance and admittance. None of the above. So this is a question with multiple options. So what do we do? We have frequency. Okay, we have ZRE, Z imaginary. We can give frequency and ZRE as the input to KKT. It will give Z imaginary measured, and this two should be similar. Then we say it is KKT compliant. So real and imaginary part of impedance? Correct. This is based on Nyquist plot. Same thing applies for the body plot, which means it also relates magnitude and phase of the impedance. Okay. Real part of impedance and admittance? No. Just real part will not help. You need to counterpart, right? So this one is wrong. None of the above is again wrong because option A and B are correct. So the answer is option A and B. Right? Now the next one is KKT is always non-tone is always sensitive to violations of linearity, stability, both neither. Yeah. So let's talk about stability. So in order to do the stability, it was explained in the video that like stability means the condition which experiment is done, it doesn't change. So your DC potential and superimposed by potential, the DC potential should not drift away. So in order to understand this, what they had done was instead of taking EDC value like this, they used a ramping potential, EDC potential. System is keeping on changing, and at the low frequency regime, we see that the system was flagged off as what to say, KKT non-compliant. So yes, stability for sure it is flagged off by the KKT. Now, what about linearity? Linearity, that means we are changing the amplitude and we seeing the response. That is when the amplitude is large enough, after a point, the impedance response changes, and it's different from that which you get when the noise, when the signal is small or the amplitude is small. So we say it's non-linear response. But it has been reported that system is non-linear. It may or may not. flag of the system as non-linear. So stability is for sure, linearity it may or may not. So the correct option is stability. Option B, because A it may or may not. Okay. Now question 5. Impedance response from a circuit consisting passive elements is KKT compliant if perturbation is small, is KKT compliant if multi-sign is applied, always KKT compliant. Option D is never KKT compliant. So sometimes it will be difficult to get the data over the entire range of frequency. So as it is required for KKT compliant test. So we may truncate it. When you're truncating it, it says it's non-compliant. So sometimes it becomes difficult to collect the data over the entire range of frequency. So what we can do is we can try to fit the data using some passive elements like resistor, capacitor, inductor and all. And if that set of data is fitted well using these passive elements, we can automatically say that the system is KKT compliant. So uh, there is no response like the effect of perturbation there because whatever data you get, you're trying to fit it into the you're trying to fit it using the passive elements. So it is always KKT compliant. So option C. Yeah. Now let's move on to the next question. Question 6. If potential instability is present, then the effect manifests mainly in options high frequency, option B low frequency, option C both of the above, or option D none of the above. So if potential instability is present, then the effect may manifest it. So we have already seen this. Unstable. So instead of applying a constant EDC, they are ramping it. And we also wrote in low frequency, the model and the experimental data will show deviation, which indicates a violation of stability. So, yeah, it is similar to question 4. I mean, the answer was. So, it is shown in low frequency. So, option B. Now, question 7. If the real part of impedance spectrum has negative values, they can be converted to positive values by option A, adding a large enough capacitor in series. Option B, adding large enough resistor in parallel. Adding small enough resistor in series. D, adding small enough resistor in parallel. So, like the real part is negative. So, in order to overcome that, what we can do is what we have to do. So, it was directly given before, that is, add a small resistor which is in parallel so as to shift the entire thing to positive. Okay. So, yeah, option B. Now, question number 8. In measurement model approach, data can be fitted using Maxwell circuit. Void circuit. Option C, ladder. Option D, none of the above. So this is multiple choice. I mean, you can select multiple options. So yeah, we already saw what is measurement model approach. So if you don't have data over the entire range of frequency, you can probably go for a measurement model approach where you're using passive elements like resistor, capacitor, or inductor in order to fit the data, right? Mm, okay, so yeah, that's about that. Now, what are ladder? What are Maxwell? Because we just came onto this, we'll just see. So, in void element, void circuit, we have initially a resistor. So, we had already seen the first class. This resistor corresponds to the solution resistance. So, that's always added in the first place. Now, after that, the void element is you have a resistor in parallel to a capacitor and multiple of such in parallel. Okay. We say it is void circuit. Now next one is Maxwell. Maxwell, again it has this one, and then it has a capacitor and a resistor, similar to this, right? Here also you have a resistor and capacitor in parallel. Same way here also you have capacitor and resistor. But that's not just it. Okay, this part is similar. Now after that, this entire thing repeats by itself in series. You have the next set of resistor and capacitors in parallel in series. Okay, so this is Maxwell. I hope that is clear. Now the next one is ladder. Ladder is something that looks like a ladder. That's why it's named. You have a resistor, you have a capacitor, you have a resistor. Now instead of having them again in series, I mean parallel after that, we are gonna have them in parallel just like in void, but in a different way. Here, now again to this resistor, you will have another resistor and capacitor in parallel. To this, you will again have another resistor and capacitor in parallel, and this continues. Okay. Yeah, this just keeps on continuing. This is called a ladder. So, in measurement model approach, you can use passive elements in order to fit the data if KKT is not working. So, I told Maxwell can work, Void can work, ladder. Why? They all have the passive elements. So, Maxwell is correct, option B, Void is correct, ladder is correct. None of the above is wrong. So, option A, B, and C. Okay. Now, question 9. If impedance spectra is acquired at wave frequency per decade, logarithmically spaced, then the following validation technique will not be suitable. So, if the impedance spectrum is acquired at 3 frequency per decade, logarithmically spaced, then the following technique will not be suitable. Just keep in mind it's not be suitable. Not will be suitable, but will not be suitable. And the options measurement model approach. Next, the linear KKT. Linear KKT is something similar to KKT, but not similar to KKT, but we'll be seeing that in the next coming uh, uh, session. Direct integration of KKT in impedance mode. Option B, direct integration of KKT in admittance mode. So we have already, there's also multiple options, not single option. If you have more than one, you can go for that. So where is it not suitable? So we already know when they don't have enough data, the KKT cannot be done properly, right? So the option because of that becomes direct integration of KKT in impedance format or in the admittance form. Option C and B. Now the last question, question 10. And EIS data is shown in complex plane plot. I will be drawing now. Below was acquired, was believed to be acquired from a stable system, and the perturbation amplitude was small. However, when it was validated with KKT, transform data didn't match impedance data, especially at low frequency, and the results shown below. Okay, they're showing a plot which if I draw, they have minus Z imaginary versus Z real. Okay, and the data being something like this form. Okay, this is the data. Now, when they're doing the Z real versus frequency, their original data is of this form, but their KKT fitting data in the low frequency regime, it is like this, and it is not matching well at the low frequency regime. Same way for their what to say, their experiment data is shown in red, and the phase value for the same is shown like this. That is their kind of mirror image. They're not. It doesn't have. It's not about fitting, but it's not mirror image. Okay. So the question is the reason for mismatch. I hope the figure is clear. So you are actually getting a mirror image and not a correct fit. The reason for mismatch is option A. Data was acquired in limited frequency range. Option B. Data integration by KKT was used. Option C. Data was transformed in impedance form. None of the above. So here, data was acquired in a limited frequency range. In that case, what should happen? Now, let's see, the multiple options are given and only one of them is correct. Okay, there's not multi-choice question, but one of the correct answers there. So data was acquired only in the limited frequency range. Then fit will be poor. For that range of frequency, the KKT fitting will be very poor. The measured value and experimental value will not meet each other. Is that something that we are observing now? No, it is a mirror image and not poor fitting. Now, poor fitting meaning you have some data like this, okay, and your fit is something like this. So this you can say it's a poor fit. But here what you see is a mirror image. Data integration by KKT was used. So if you are doing KKT, if there is any issue in the data, what you will again see is poor fit. Okay, if KKT is not done correctly, a fit will be poor. But as mentioned before, it's not the poor fit that you're observing. Data was transformed in impedance. Yes, we did learn earlier that if you have data, the ZRE value going to negative, okay, or second quadrant, in that case, if you are using impedance form of KKT transformation, you will get mirror image. Okay, so that is what you are seeing here. Then what is the right way to do? The right way to do is transform the data admittance form and then do KKT. If you do, you will get the correct fit. None of the above is not possible. So answer is option C. Yeah. So that's all about assignment 3. Now next week we'll be discussing about assignment 4 once that's done. Okay. So more like next class we'll be looking into measurement model approach where you will be using both the passive elements like resistor, capacitor, inductor. Now we'll be learning more about the void circuit, then a void circuit, and then Maxwell ladder circuit. Then after that, we'll be seeing how to interpret from the impedance data, like how many loops are there, how do you correlate it to the or relate it to the passive element circuits. Then like how many such circuits do you need, or how many components you need in order to fit a circuit? What is the right amount, and what is actually so much, that you will understand in the next chapter. And there we'll also learn about distinguishability. Distinguishability is like if you have two circuits, like if you have a what circuit with two RC, then that is similar to another Maxwell where you have two RC, similar to another ladder with two RC. So if you have values in two RCs of a ladder, that values will not be same here for both of them to be similar. The values may change. But how do we find that out? So that is again seen in the next chapter. Then we also see about zeros and pole representation. Yeah. So with that, we'll be mostly covering the fitting of the impedance model using the electric circuit elements. Later on, so that is about this week's assignment. Then we'll be moving to mechanism prediction. Yes. So I hope this class was useful for everyone. Okay. Thank you everyone for patiently listening. Okay. So I'm now stopping to share. Yeah. So we'll now meet next class and we'll be discussing assignment number 4. Okay. Thank you all. Thank you.